Hey guys! Today we're taking a look at physically based rendering for the second time. I have a video on PBR from almost 3 years ago, so I decided it's time to take a fresh look at the subject. That video was based on an implementation from the OpenGL 4 shading language cookbook, and today's video will be based on another cookbook, 3D graphics rendering, which in the second edition actually focuses on Vulkan. We will be using OpenGL, which is simpler and will allow us to focus on the shader side. The plan is to use pretty much the same shaders in Vulkan once its tutorial series is ready for it. Now, a key element in this implementation is the GLTF2 shading model. GLTF stands for Graphics Library Transmission Format. This is yet another file format for storing 3D models, which was introduced by Khronos in 2015. The fact that it is open source makes it very attractive for adoption by the various modeling tools and graphics pipelines, because it is not under the control of a single company. GLTF is available in text format as a JSON file, as well as binary files. We're going to work exclusively on the second version of GLTF, where PBR support is one of the major features. The advantage of PBR as an extension to GLTF is the standardization of something which was previously prone to inconsistencies between its early adopters. Both Blender and the Assimp library support importing from text and binary GLTF files. Before we get started, I'd like to say a big thank you to Tim, who recently joined the 3D Underground. If you too would like to support this channel, you can do that at patreon.com/ogldev or by joining the YouTube channel as a member. There are two major workflows in PBR, metallic roughness and specular glossiness. Due to time constraints, we will only be able to study the first of these. The metallic roughness workflow is based on three key textures or parameters. A base color map, also known as albedo. For non-metals or dielectrics, it stores the diffuse color, and for metals, it stores a specular color. A metallic map, this is a grayscale map that indicates whether a texel belongs to a metal or not. 0 is non-metal, such as plastic or wood, and 1 is for metals. Intermediate values are rare and usually avoided, since a material can either be metal or not. And the last one is the roughness map. This map contains floating points, which can go from 0 or perfectly smooth up to 1 or very rough. We start by upgrading our support for the Assimp library. Check my previous tutorials on that, because here we will only focus on the changes for PBR. First of all, we expand the vertex structure with a second texture coordinate. According to the GLTF, a vertex can define up to 8 sets of texture coordinates. The first one is usually used for the base color, normal, and etc. The second texture coordinate is for stuff like ambient occlusion, light maps, or detailed textures. The last 6 coordinates are for custom shader effects. So for now, 2 sets will do. In addition, there is a new color attribute, which will be used in the Fragment Shader to calculate the final color. The next change is in the material class. Remember that in Assimp we have an array of meshes, and each mesh includes an index into an array of materials. Previously, I maintained pointers to the diffuse, normal, and specular exponent textures. But PBR needs more textures, so I changed this to an array of pointers to textures, where each index references a texture type. The size of the array is currently 9, and it now includes additional textures, such as metalness, emissive, roughness, and a few others. The material class also includes a base color and emissive color, as well as 2 floating point parameters, a transparency factor and an alpha test. Loading these values takes place in the core model class. I have a wrapper function called loadColor, which calls the get function on the Assimp AI material structure. Assimp provides a few macros for specifying the colors, the alpha cut, opacity, and color transparency. Notice how the alpha cut is set into the alpha channel of the emissive color. Make sure to review this piece of code and adapt it to your own engine. Loading the textures has its own set of functions. In general, each texture can be loaded from its own file or from the binary file itself as an embedded texture. The core model class supports both methods of texture loading. To load a texture, we call getTexture on the Assimp material structure using the correct texture type. Assimp provides quite a few texture types, and some of them are specifically intended for PBR support. The PBR Vertex Shader is the same one that we used for the Phong lighting model. Just make sure to update it with the new vertex attributes, the second texture coordinate, and the color. Most of the work is in the Fragment Shader. It begins by setting up the input attribute structure. This is simply a combination of the two texture coordinates. Next, we fetch the material structure. In the case of indirect rendering, this info comes from its own SSBO. If not, we fill up a material structure using the uniform variables and return it to the caller. We now sample 5 textures: ambient occlusion, emissive, albedo, metal roughness, and the normal map. We can now calculate normal mapping, and if you need more details, then I have an entire video on that. The next function call is kind of a utility function. It calculates a few pieces of information that we will need for the algorithm. Those pieces are wrapped in a structure called PBR info. It contains a few dot products between various vectors, the bump mapping normal, the vector from the pixel to the camera, and a few material parameters. The next 2 function calls calculate the diffuse and specular lighting. Take a look at these elements separately before we combine them together into a single vector called color. This is where the core of the PBR calculation takes place. The next function calculates the contribution of a single directional light. We can now modulate the color by the ambient occlusion factor and add the color from the emissive texture. Finally, we convert from a linear color space to sRGB. Notice the difference between the two color spaces. I think sRGB looks much better. So now let's take a closer look at calculate PBR input's metallic roughness. This function starts by extracting and clamping the metallic and roughness factors. These 2 factors are part of the material definition in GLTF2. Our material structure packs a few factors into a single vec4: metallic factor, roughness, normal scale, and occlusion. We need to modulate the metallic factor by the blue channel of the metallic roughness texture. A common optimization in a PBR pipeline is to pack a few per pixel elements together into the same texture: the ambient occlusion in the red channel, roughness in the green, and metallic in the blue. The ambient occlusion in our case is actually provided by a separate texture, so we will only use the remaining 2 channels here. After modulating the metallic factor, we clamp it to a valid range. We do the same thing with roughness, and we also clamp it to a minimum of 0.04 to avoid division by 0 or too extreme sharp reflections. We also raise roughness to the power of 2 because, well, Disney found out it works better. Next, we use the color from the albedo texture to calculate the base diffuse and specular colors. These elements will be stored in the structure we return from this function and will be used later on. We use the metallic factor to mix between albedo and 0 for the diffuse color and between 0.04 and albedo for the specular color. Now comes the reflectance for the Schlick approximation of the Fresnel equations. We take the maximum channel in the specular color and scale it up to simulate stronger reflectance at grazing angles. Finally, we calculate the dot product between the normal vector and the vector from the pixel to the camera in world space, aka the view vector. Notice that we clamp it to avoid division by 0. The n.v attribute will be used in several places in this shader. All this data is saved into a PBR input structure, which will be returned to the caller. The last thing we have to do here is to calculate the Schlick approximation for the Fresnel reflectance, and we have a dedicated function for that, which takes a PBR input structure as a parameter. This type of reflectance describes how much light is reflected versus refracted when it hits a surface. It basically depends on the angle of incidence and the material refractive index. In the previous video, we saw a common implementation of the Schlick approximation, which is often used for real-time rendering. In this video, we have a slight change introduced by Carmelo Aguera in a 2019 paper. This change is supposed to somewhat increase the reflectance of rougher surfaces, as you can see in the following example. The way we approximate the Fresnel equations brings us to the topic of the bidirectional reflectance distribution function, or BRDF. This is a generic name for a function which calculates how light is reflected off a surface. To calculate the BRDF, we need to integrate it over a hemisphere around a point on the surface. But since this calculation can eat up substantial compute resources, it is a common practice to pre-compute the BRDF offline and store the results in a lookup texture to be used during runtime. This can significantly improve the performance of the algorithm. The lookup texture is model agnostic, so we only need to do this once and reuse it for all assets in the scene. The texture encodes the results of integrating the BRDF for a range of view angles, as well as different surface roughness values. These are general properties in PBR, which are not specific to any model or material. The lookup table is a 2D texture, where the x-axis is the dot product between the view vector and the normal, and y is the perceptual roughness of the surface. Each texel in the lookup table includes both the scale and bias terms used in the Fresnel approximation. In this video, we won't be going into the creation of the table, so you can simply use the one from my repo. The next step is to construct the textural coordinates from n.v and the perceptual roughness from the previous function. We clamp it between 0 and 1, and we use it to sample the BRDF texture. The texel which is sampled contains the scale in the first component and the bias in the second. The scale and bias will be used in another function in addition to this one, so we cache them in the PBR input structure. The next 3 lines calculate the Fresnel term. It is returned to the caller, who stores it in the PBR input structure as well, because it is used for both the diffuse and specular reflections. Now let's see how to calculate the specular color in the function getIBL_radiance contribution ggx. Notice the acronyms IBL and ggx. IBL stands for image-based lighting, which is a rendering technique that uses images, typically environment maps, to light a 3D scene. We have previously used environment maps for cube mapping and skyboxes. So instead of having an individual light source with some constant color, IBL allows us to capture the full lighting environment and use it to illuminate objects in a physically realistic way. It is often used in PBR pipelines, which is exactly what we're going to do. GGX is a microfacet model which simulates how light reflects off a rough surface. We talked about the microfacet theory in the previous PBR video, so just a quick recap. The idea is that a rough surface is made up of many tiny microfacets, where each microfacet acts like a perfect mirror. The overall result depends on the statistical nature of all these reflections. We start by reflecting the view vector over the normal. Since this is a specular light, the light ray hits the surface and bounces off into the viewer's eyes. So we want this pixel to have a color from the corresponding part of the environment. This means we need to reverse this process in order to get a vector to sample from the environment map. Notice that the view vector is in the negative. This is because it goes from the pixel to the camera, whereas the reflect function needs the reflected vector to point into the surface. Next we get the info structure from the environment SSBO. This buffer contains the handles of a few environment textures that we will need. We get the number of mipmap levels from the environment map using the GLSL function texture query levels, and we use the perceptual roughness fraction, which was calculated in the previous function, in order to calculate the specific LOD to sample. We use the reflection vector and the LOD to sample from the environment map. Notice the GLSL function that we use here, texture LOD. This function takes a sampler handle, texture coordinates, and the LOD to sample from. Depending on the LOD, this will simulate the blurred reflection caused by the surface roughness. We can now compute an approximation for the environment specular contribution. Since we're using the pre-computed lookup table, we don't need to do any integration at this point. Remember that the Fresnel term was already calculated and cached in the PBR input structure, so we just need to multiply it by the color which we sampled from the environment map, and this is our specular color. The next big step is the calculation of the diffuse color. The following function handles multiple light scattering, which means that light doesn't necessarily bounces off a surface in one clean bounce. Instead, it can bounce around some microfacets on a rough surface before it exits towards the viewer. This means that we don't assume that light will get lost after a specular bounce. In fact, this function returns some energy back into the diffuse path. It makes the materials more realistic and not unnaturally dim. To summarize, multiple scattering addresses the resilience of light on a bumpy surface. For this function to work efficiently, we will use yet another pre-computed cube map called an Irradiance map. This cube map encodes the diffuse part of the environment. It tells us how much light is arriving from all directions on the upper hemisphere. Think of it as a blurred version of the environment map. Again, we won't be going over the details of creating this texture because we simply don't have enough time here. We start this calculation by sampling the Irradiance map using the normal. This gives us the incoming light from all directions. Next, we calculate the energy of multiple scattering, or EMS. This is basically the leftover energy after some of the light bounces around the microfacets. The BRDF scale and bias represent the specular light, and adding them together might seem a bit unconventional, but we just want to approximate the specular energy which was already consumed. The next line calculates the average Fresnel reflectance over all possible view directions. Reflectance 0 is the base Fresnel reflectance at normal incidence. This is usually 0.04 for dielectrics and close to 1 for metals. Since the Fresnel effect increases at grazing angles, subtracting reflectance 0 from 1 gives us the potential of this increase. Basically, the remainder. We divide the remainder by the magic number 21. This is an empirical constant which comes from a lot of research and trial and error by many people. It compresses the integration of Fresnel over the hemisphere into a single scale factor, and as always, it is an approximation intended to get rid of expensive computation. The next line reintroduces light back into the system, which would otherwise be lost due to microfacet occlusion and imperfect reflection. The denominator is an estimation of the energy that is trying to escape after multiple internal bounces, shaped by how reflective the surface is and how much energy is still in play. The denominator is there to prevent us from exceeding physical energy limits. Next, we calculate the effective diffuse reflectance. We subtract the single scattering specular energy from 1 to get the remainder, and we multiply it by the base color. But this is too simplistic, so we add back the energy from multiple scattering. This ensures the material doesn't look unnaturally dark. The last line in this function calculates the final values of diffused light. We add the multiple scattering energy factor to the effective diffuse reflectance and multiply the result by the ambient light we sampled from the environment. At this point, we have the diffuse and specular terms that are the result of the environment, basically an ambient light source. We are now going to calculate the effect of a single directional light. This is the job of the following function. We start by calculating the halfway vector between the view vector and the light vector. This is the same vector used in the Blin-Fong reflection model. Next, we calculate a set of dot products between the normal, light vector, view vector, and the halfway vector. These will be used throughout this function. As usual with diffuse light, we only calculate its contribution if the angle between the light direction and the normal is less than 90 degrees. In this case, we have an additional check for the angle between the normal and the view vector to make sure the surface is even visible. The calculation itself is composed of 3 terms: the specular reflection, the diffuse reflection, and the cosine-weighted light energy. The specular reflection is calculated using a slight variation of the Schlick approximation of the Fresnel equations. Instead of using 1 here, we have reflectance 90, which represents the reflectance at grazing angles. Using a variable here allows more control to the artist and is especially important for materials such as skin, cloth, and hair. Remember that reflectance 90 was calculated in an earlier stage of this tutorial. The next function calculates the geometric attenuation term in the microfacet specular BRDF. This is an estimation of how the roughness of the surface reduces the amount of light which is reflected directly towards the viewer. The equation here is based on the Smith geometric attenuation function with some modifications by Epic and Disney. In a nutshell, the formula controls how much of the surface is visible to light or camera based on the angle and roughness of the surface. The third term is an approximation of the GGX normal distribution function. This function estimates how likely it is that the microfacet is oriented to reflect light towards the viewer. This version is known as Trowbridge-Wrights, and we've seen it in the previous PBR tutorial. Due to lack of time, I'm going to skip it for now. We can now calculate the diffuse and specular contribution of the light source. The Fresnel term represents the specular reflection, so the remainder, after subtracting it from 1, is the diffuse part. The function diffuse Burley is a modification by Disney of the Lambertian model. The specular contribution is the classic Cook-Torrance microfacet specular BRDF, which we saw in the previous video, so we will skip this one as well. The final calculation is also the same as the previous tutorial. combine the diffuse and specular contributions together, multiply it by the color of light, and adjust it based on the angle of incidence. And that's it for today. Don't worry if you don't get an intuitive understanding of all the details. Remember that everything that we saw here today is the result of many years of research by computer graphics PhDs. So this was just an attempt to scratch the surface of physically based rendering. Thank you for watching, and I will see you next time.